So now we are down to our last speaker. So Professor Gary Brudvig. So Professor Gary is the Benjamin Silliman Professor of Chemistry, Professor of Molecular Biophysics and Chemistry, and the Director of the Yale Energy Sciences Institute. He received his bachelor's degree from the University of Minnesota and his PhD from Caltech, and was a Miller postdoctoral fellow at the University of California. He is the founding director of the Energy Sciences Institute located at Yale's West Campus, where he oversees the development of new research programs and facilitates related renewable energy, alternative fuels, and carbon management. Please welcome Professor Gary.
Hello, everyone. My name is Gary Brudvig. I'm very pleased to present. And I'm going to present on behalf of the Institute of Physics. They publish the journals Nanotechnology and Nanofutures. I'm on the executive editorial board of both of these, where I cover areas of research on artificial photosynthesis, solar fuels, and water oxidation. So I'm glad to be able to present on behalf of them. And let me introduce my talk. I will talk about water oxidation catalysis with atomically defined active sites on nanostructured materials for solar energy applications. This is work we do at Yale University in the Department of Chemistry in the Energy Science Institute. So here's a picture of the chemistry building, and it's on Yale's main campus. And this is a picture of Yale's West Campus. This was formerly the research and development site of Bayer Pharmaceuticals, and Yale purchased the site, and we've used it to create interdisciplinary research institutes. I've been the founding director of the Energy Science Institute for the past 11 years, where we've created research programs aimed at fundamental research for energy applications. And this is a really outstanding environment. We have about 100 researchers working in a common space, and these people come from more than 6 different physical science departments, and we carry out interdisciplinary energy research and call Under One Roof, where we have great opportunities for collaborative projects and strong interactions between different groups and to carry out interdisciplinary research. These are the PIs that carry out the work at the Energy Science Institute. We have people like myself working on energy production and storage, particularly solar energy. We have 4 theorists who work very closely with the experimental groups. We have a number of groups that carry out measurements or work on devices. And we also have a very strong materials research group, particularly focused on quantum materials. So I'm going to talk about the work that my group does. And this is a collaborative effort that involves 4 faculty from the chemistry department at Yale. Victor Batista, who's a computational chemist, myself, Bob Crabtree, who's an inorganic chemist, and Charlie Schmittenmeyer, who does ultrafast terahertz spectroscopy. Unfortunately, Charlie passed away a couple of years ago, but his research carries on, and I'll talk about research that involves him as well as the rest of us. And our focus is to design catalysts, develop ways to attach them to metal oxides like titanium dioxide, with the focus of carrying out solar fuel production using visible light to produce high energy chemicals that can store the energy of sunlight in the form of chemical bonds. And we have a very strong experiment and theory collaboration. Of course, Victor Batista is a computational chemist. We work very closely. The experimental groups work very closely. Here's Charlie Schmittenmeyer, myself, together to use theory both on the input side to design experiments, but also on the output side to interpret the results. And we've gained a lot of experience on how this can be done effectively. And with that experience, we wrote a review article on how collaborations between experiment and theory can develop. And we've described case studies for successful collaborations. And if you're interested, you can check that out. Our work is, I would call, bio-inspired artificial photosynthesis. So, of course, nature is the only global process for storing solar energy in chemical bonds. And it does that by using light to drive water oxidation on the and Oxide, and transporting electrons and protons to other sites where fuel forming chemistry is occurring to store the energy of sunlight in chemical bonds. We're not trying to replicate the structures exactly, but we'd like to understand the design principles and apply them for artificial processes that could have higher efficiency and greater stability. And we're focused on using nanoporous metal oxide materials like titanium oxide nanoparticles, and we're designing catalysts to carry out the water oxidation reaction. Of course, in this overall process, the water oxidation reaction is the challenging reaction. It's mechanistically complex, and it's often the bottleneck for overall water splitting. And so we've focused on developing the photoanode, where we have water oxidation catalysts attached to these metal oxide materials. And this is kind of a schematic of the design. So we'd like to have a light-induced charge injection where electrons are injected into the conduction band, can be transported through a photoelectrochemical cell to be used for fuel-forming chemistry like hydrogen evolution. And we're interested in molecular catalysts for this process. And so we need to have chemistry for attaching molecular complexes to the surface of metal oxide materials. We need to have anchoring chemistry to covalently bind them to the surface, and linking chemistry. And so I'd like to talk today about some of the work we've been doing on anchoring chemistry, and then also the catalyst design and attachment for light-driven water oxidation. So for the basic idea then for anchoring chemistry is we've got a metal oxide surface, some kind of nanoparticular structure, nanoparticle, nanotubes of various sizes. And we've used insight from nature to design chelating groups such as catechol and hydroxamic acid, which are used as natural products for binding strongly to metal complexes. We've also used inorganic complexes like acetylacetone or ACAC or chelating groups that can attach to the surface. We link them to catalysts, and one example is this manganese to pyridine complex that Bob Crabtree and I reported previously to be able to carry out the light-driven water oxidation. More recently, we've been working on a mode of attachment using a molecule called a silatrane. So this is an example of a silatrane. It's a siloxane molecule, but it's protected by this triethanolamine molecule. So it's not reactive. It allows us to be able to incorporate this anchoring group to a molecular complex and carry out synthetic steps, either for dye synthesis or catalyst synthesis. And then by using mild heat, we can deprotect and attach it to the surface using silicon oxygen bonds to the metal oxide. Very robust attachment. This linkage is stable over a pH range from 2 to 11. And it's also both oxidatively stable and reductively stable. And so this has been really significant. It's much more effective than just the siloxane itself, which is very difficult to handle synthetically and also is very challenging to put down on a surface in a well-defined way because it polymerizes so readily. One thing we've realized recently is that the protecting group, this triethanolamine protecting group, remains attached to the surface when we carry out this mild heating step. But we can remove it by an acid wash. And what this does is it exposes another binding site exactly adjacent to the first molecule that allows us to pattern the surface where we can put down a catalyst, for example, with a siloxane anchor. And then we can put a dye right next to it with, for example, a phosphonic acid attachment. And this allows the photochemical process to be done much more efficiently, where the dye can inject an electron into the conduction band of the metal oxide and then very efficiently transport holes to the catalyst because of the adjacency. And this is something we're very much working on right now. But today I want to spend most of my time talking about water oxidation. So we can catalyze a reaction using a molecular complex in homogeneous solution. It has advantages. It can tunable or easy to characterize using chemical methods of molecular structure determination. They often have very high efficiency, and they are amenable to rational design where we can iteratively optimize the performance. But the disadvantages, they're often unstable. And one I can highlight the instability by comparing the bond association energies. The bond of OH bond of water is stronger than any CH bond in an organic molecule. So if we have a molecular complex with stage bonds, they're going to always be easier to oxidize than water. And this is in fact reflected by the fact that if we carry out the water oxidation reaction in solution, water oxidation catalysts do not last very long, and it's led to the conclusion that they're going to be unstable. On the other hand, heterogeneous catalysts, such as metal oxides, can be much more stable. But the drawbacks is that they often have low catalytic efficiency, and the design is often empirical. So what I'll describe today is how we can maintain the high efficiency of a molecular catalyst, but overcome the instability by attaching it to a surface, so heterogenizing the molecular catalyst by using anchoring chemistry to attach it to an oxide surface, then combines very high stability and also high efficiency. So to begin, here are some of the early reports of molecular catalysts for water oxidation. The first was a ruthenium dinuclear complex that was reported by Tom Meyer's group in the 1980s. Bob Crabtree and I reported this manganese terpyridine complex in 1999, which remains the fastest turnover of manganese catalyst for water oxidation. Both these are based on manganese and ruthenium. And one of the things I'd like to highlight is that the choice of metal ions. So nature had the choice, I would say, of any of the first row metal ions, and it chose manganese as its catalyst for water oxidation. That's one of the reasons we focused on manganese catalysis. And this one of the other features of this diagram shows the diagonal rule of inorganic chemistry. And that is, if you want to identify the metal ion that has the most similar chemistry on a second row, you go down to the second row and over one, and that's ruthenium. Of course, ruthenium is the overwhelming choice for water oxidation catalysis. And if you go down to the third row and over, it's iridium. Of course, it's been known for many years that iridium oxide is the best oxide catalyst, but it's only relatively more recently that molecular iridium complexes have been studied. And the first report was by Stefan Bernhard in 2008, with phenylpyridine iridium complex. And we've worked to identify, we want to achieve a complex with high stability and also high catalytic activity. And we found this chelating ligand, we call it PyAlk, or the pyridine and alkoxide groups, is really a winner. It combines chelating stability with the hydroxyl group, which of the alcohol, which can deprotonate to facilitate proton-coupled chemistry, proton-coupled electron transfer chemistry. And it also in the deprotonated form, the alkoxide very strongly favors the high oxidation states of metal ions, which are necessary to achieve in order to catalyze the oxidation of water. And we wrote a review article on this to describe some of the applications. So I'll just describe our best catalyst to date is this iridium dimer. We can form it from a iridium precatalyst. It's iridium pyridine-alkoxide complex with a CP star ligand. And we can either chemically or electrochemically oxidatively activate it to form this dinuclear iridium complex, which we call our blue solution species. And we can illustrate its catalytic activity by showing the evolved oxygen as a function of time after we apply a voltage. And you can see very fast oxygen evolution in the case of the activated species, this blue solution species, and essentially no oxygen evolution for this precast, although we have shown that this is in fact a water oxidation catalyst. It's just that it's so much slower than this dinuclear complex that it doesn't show up on this trace. So now we'd like to put it on a surface or heterogenize it by attaching it to a metal oxide surface. And this is actually quite easy to do for this complex because it spontaneously absorbs to metal oxides. So here's a blue sample of our blue solution. This is dinuclear iridium complex. We can soak a mesoporous metal oxide film in this solution, and it will spontaneously adsorb on the surface. So titanium oxide, tin oxide, tungsten oxide, and iron oxide. It's very strongly adsorbed. So in the case of titanium oxide, we found that the only conditions which will remove the catalyst from the surface are conditions that dissolve titanium oxide. So it's very tightly bound. We believe it's grafted onto the surface through a very strong titanium oxygen iridium bonds. Of course, this now allows us to carry out electrochemistry by using a conducting oxide electrode, nano-ITO, to carry out cyclic voltammetry. And this blue trace shows the cyclic voltammogram of the adsorbed catalyst on the surface. And what we see is a reversible iridium 3,4 couple, followed by a catalytic wave with an onset that is essentially right at the thermodynamic potential. So it's a very low overpotential for this catalyst. And it's also extremely stable. I won't show here, but we published that we can carry out 100,000 turnovers and identify using spectroscopy, X-ray photoelectron spectroscopy in particular, that the catalyst has not undergone any decomposition over that number of turnovers. We then use this catalyst in a variety of ways. One of them is to put it on the surface of hematite to improve the catalysis for water oxidation of hematite. And this is work we've done in collaboration with Dongwei Wang's group at Boston College. So we can put a monolayer of this molecular catalyst on hematite and examine the photocurrent as a function of applied voltage. And you can see that the molecular catalyst on the surface significantly improves the onset, cathodically shifting it by about 0.25 volts compared to just bare hematite. We've also used this to create a complete solar water splitting system that works in acidic solution at pH 1. And this is a system where we use hematite with our iridium catalyst, blue solution catalyst anchored on the surface. And we use an amorphous silicon photocathode. And here's a design. So here's the photoanode with our iridium catalyst. It absorbs the shorter wave visible wavelengths to carry out light-driven water oxidation. And then the cathode absorbs the near IR radiation to carry out light-driven hydrogen evolution. And you can see the measured hydrogen oxygen, which occurs with essentially 100% Faradaic efficiency with no bias voltage. So this is something that demonstrates the potential for these molecular catalysts. We've also examined not only the catalytic performance, but also the structure on the surface. So this again shows the photocurrent as a function of applied voltage. But in this case, we're comparing not only bare hematite here in black, but iridium nanoparticles attached to the surface of the hematite, which slightly improve the performance, or single iridium atoms on the surface, which improve the performance a little bit further. But the nuclear heterogeneized catalyst, or DHC, dramatically improves the onset voltage for water oxidation, for light-driven water oxidation. The surface now can be imaged using high-resolution TEM, and this is showing the hematite lattice where we see these bright spots, two bright spots adjacent to each other. Here's the intensity profile going along this trajectory, this line here. And we see only dimers. So there's a dimer here, another dimer here. And these dimers are extremely stable. So we can image the surface both before and after photocatalysis, and the dimers haven't moved. So they're extremely tightly anchored to the surface. And because we can see the lattice, we can model it. So this is Victor Batista's group now. They can model the surface of hematite. And what we find is that the iridium are essentially superimposed over the iron. And this is a position where there are three oxygens on the surface that we believe are coordinating to the iridium in this kind of threefold way here on each of the iridiums. And the structure of the iridium dimer is nicely matched to the lattice structure of hematite, so that the second iridium can also bind to three oxygens on the surface to preserve the structure of the catalyst, which then, of course, remains very active on the surface. We can put it on other surfaces as well. And we've looked at, for example, tungsten oxide. The interesting thing about tungsten oxide is that its lattice is larger. The lattice spacing is larger, and it doesn't allow a side-on binding like we see in the case of hematite. Instead, we see end-on binding. When we image the surface, we don't see dimers, but we see only single bright spots, which we believe is because the iridium catalyst is pointing straight out. But we can confirm that it's still dinuclear by looking at the carbon monoxide frequencies in diffuse reflectance infrared spectroscopy. This was done in collaboration with Matthias Wegle and Dongwei Wang at Boston College. And what we see is a doublet of doublets, which is simulated with this structure here. indicating that we have now an end-on structure, which still is effectively catalyzing water oxidation. We can see the improvement in the photocurrent here as well. So let me just end by saying what we've learned, some of the lessons we've learned for water oxidation catalysis with atomically defined active sites on nanostructured materials. What I've shown you is that we can, by using the molecular chemistry, design and optimize molecular catalysts, and we can characterize their structure and function in homogeneous solutions so that we can have a good understanding of both the structure and mechanism of the reaction. And then we can use anchoring groups to attach the catalyst to the surface of metal oxide materials. And in the case of the silotrain anchoring group, we can use it for patterning the surface to use molecular surface chemistry to attach, for example, dyes and catalysts in adjacent proximity. And then once we've attached these molecular catalysts to the surface, we have extremely stable systems which can carry out light-driven water oxidation for many hundreds of thousands or millions of turnovers even, without degradation. And so I think this is really an exciting direction for the future, for combining the strength of molecular chemistry with the stability and efficiency of heterogenized catalysts. And so with that, I'd like to then end just to acknowledge all of the people. This is a collaborative group, and this is my own group, and we work both at the chemistry department at Yale and then in the Energy Science Institute, and this work has been supported by the U.S. Department of Energy. And with that, I'd like to end and thank you for your attention.